Okay. So, Pramod, I'll use this one.
Okay.
All right.
You can, absolutely.
So, good morning, everyone. I am Anwar from University of Wyoming. So, I think I'll be standing here in that way. We can see you better. And also, is on, right? Okay. So, again, good morning, everyone. This is my great opportunity to be here today and talking about my project. So I was talking with Alan. Thanks for nice introduction, by the way. So we have 3 presenters so far, so I am allowed to talk maybe a little bit more. And please feel free to ask me question while I am going. So if you don't know here who you are new in the USA, I am in the western part. Probably you heard the name Yellowstone. So I am close to Yellowstone area, and I am at the University of Wyoming in the plant science department. So I'll first acknowledge my grad student, Michael Baidu, who actually did all the work, and I'm presenting, taking the credit. That's not true. So I have give 100% credit to Michael Baidu. That was his PhD project, and immediately finishing his PhD project, he started in Montana. So he left, but I am giving today on behalf of him presenting this work. So why, you already know alfalfa, why alfalfa is important. We call alfalfa queen of forages, right? It's because of its high productivity and also quality. However, there is a recent trend of declining the productivity. So if you look at the trend for starting from 1920 to recent years, there was a sharp increase of productivity. Look at this from 20,000 to over about 10,000, even more, 100,000, right? So this is really good until here. It's around 1990. After that, it started to decline. So although it is queen of forests, what is happening here? Why it started to decline? So also there is a report saying that there is a decline of acreages as well in recent years. So why is happening? Why alfalfa productivity is declining, started to decline? So there are many reasons for that, although reason is not very clear. So one of the would be stand management aspects. So maybe due to poor stand management. In general, alfalfa, although it's a perennial, it can easily survive for 10 years or more, 20 years, if you manage well. However, after, for example, 3rd year, it is general trend. This is the genetics of the plants. It started to decline after 3 years. But still, it's not bad, actually. If you manage well, you can get 10 years, very high productivity. So another reason also, the stand density, along with the leaf to stem ratio. So if you have higher stem, that means you are expecting higher leaves. That means you're expecting higher productivity and quality. However, there's a certain point after that, even if you add more fertility, more management, it will not go beyond that point. Like in general, this is just a standard, around 55 stem per square foot is the standard. After that, it started to decline. So what other factors may influence in reducing the productivity and acreage of alfalfa? Another important one is agronomic management. What are those? That includes, for example, fertility replacement, right? You grow alfalfa every year and taking out every year, that means you are taking out huge amount of nutrient from the soil. If you don't replace this, that means it will be continually declining. Another one would be cutting schedule, right? So harvesting time, how many times you harvest, and if you don't harvest properly, that could be also influencing the productivity and quality. Crop genetics itself, that means variety, what variety you are going to use, that's also has important impact on productivity and quality, as well as the disease problem, pest problems, right? So that's all influence the productivity and quality. So, but today's talk will be mainly focused on fertility management and also cutting management. So another important aspect is the balanced nutrition of specifically phosphorus and potassium. So this is just an example, and in California, they harvest a lot of times, like this is 5 harvest. So in the left-hand side, this is the control. That is, you did not apply any P and K, phosphorus and potassium. And these are the combination of adding phosphorus only, or adding potassium only, or adding phosphorus and potassium in combination. So you can see here control to up to 7% adding only phosphorus, to P and K up to 42% increase. So there is no doubt balanced phosphorus and potassium can increase productivity significantly. So on the other hand, you have to look at the price of the potassium. It's skyrocketing, right? So if you look at this, in 2016 it was about $300 per ton compared to about $1,000 in recent price. So when you add, because alfalfa is a potassium-loving crop, if you add more potassium, it will take more potassium. But you have to look at also economics, whether adding potassium would be beneficial or not. Another important aspect is the current fertility status in the soil. So if you have more potassium, do I need to add more potassium? If you have already phosphorus, do I need to add more phosphorus on this soil? So because current potassium and phosphorus level also influence the uptake and productivity of alfalfa. Another important aspect is soil pH. Like we have soil expert here, I am not talking too much on this. However, pH play an important role in the availability of phosphorus. So in addition to calcium and magnesium as well. So we have to look at also. So alfalfa does not like acidic soil. If it is below 6, alfalfa is not good fit. You have to increase the soil pH. On the other hand, if it is too high pH, so then alfalfa will not be a good crop for this growing. So we have to make sure that pH is right pH for growing alfalfa. And another important factor is the valency of potassium and other bivalency as well. So it's normally reports suggest that if you have more calcium and magnesium in the soil, you might need to add more potassium as well. So then balanced application of phosphorus and potassium also influence the uptake and availability of other nutrients. This is true fact. So we have to look at all the factors as well, why alfalfa productivity is declining. Also, calcium and magnesium, if we have high level of calcium and magnesium at the soil, do I need to add more potassium or more phosphorus in the soil as well? So that's another question. Maybe many reports suggest that's true, that you have to add more potassium in the soil. So also time of harvest, it is important factor, not only alfalfa, in any other crops, grass, no matter what it is. So for example, in alfalfa, this is the growing space and this is the productivity. So if you allow the alfalfa plants or any other plants to grow more longer time, you are expecting the productivity will be increased. On the other hand, there is a trade-off, right? The quality would be declined. So we have to find the right place where the productivity and quality can be optimized. So then, another factor is, especially we have to explore more the response of alfalfa to balance nutrition of P and K, and also magnesium and calcium along with the harvest time. So this generates the question. First question is, will alfalfa respond to potassium and phosphorus in soil with high level of potassium? This is where I am from Wyoming. In the western part, most of the western part, potassium is not a factor, it's not limiting factor. Potassium and phosphorus always available. However, some soil, we add potassium, we get response. Some soil, we don't. So that's we need to explore. The question is, if we have high level of potassium and phosphorus in the soil, do we really need to add potassium in the soil? Also, another question is, will alfalfa respond to potassium and phosphorus nutrition in soil with high level of calcium and magnesium. And then third question is, what will be the effect of phosphorus and potassium in association of calcium and magnesium, and also harvest time. So that's the combination, complicated factors, what will be happening over there. So our specific goal, the goal of this project was to determine whether phosphorus, potassium, calcium, magnesium, and harvest time interaction will affect forage accumulation, then nutritive value as well as stand persistence of alfalfa. And then we hypothesized that all this nutrient along with harvest time interaction will have positive impact of alfalfa productivity. And then our specific goal that we want to evaluate specifically the interaction effect of all these nutrients along with harvest time, not only productivity and also economic benefits, whether is there any financial benefit adding all those. So now how we did that, the experiment was conducted. This is a multi-state project of NIFA funded project. So there are 4 states involved on this. It was Wyoming, Colorado, then also Oregon, and also Kansas. So I am reporting only here Wyoming results today. So there are 18 treatment combinations. That's coming from 3 levels of phosphorus, that is control 34 and 67 Sp2O5 per hectare. Then 3 levels of potassium, 168 and 336. And then 2 rates of calcium and magnesium. And that's the combination. It's a 18 factor. That means it started 18 treatments combination. Starting from control, we did not add anything at all. Then increasing level of phosphorus, increasing level of potassium, then combination of phosphorus and potassium along with, this is the highest treatment of every element, phosphorus, potassium, calcium, and magnesium. And then we have 2 harvest time. One was early harvest versus late harvest. So early harvest is actually standard harvesting time when we have more productivity and quality. That's about late bud to 10% blooming. And then the late harvest is about 7 days after the early harvest. So then, of course, this is a factorial design because we have so many factors on that. So initial soil sampling was conducted about 0 to 15 centimeter depth. And then initial fertilization occurred in the fall of 2019. And planting, we used High-Zest 361 of the latest variety of alfalfa from Alforex. Seeding rate, very standard, 22 kilogram per hectare. And you can see here how we planted in September, early September 2019. Then just a month later, you can see started to come up all this seedling. You can see that. In next year, in the spring, you can see it's getting very nicely coming up. And before harvesting in June, you can see very good stand established over there. Can you see the picture from the back? Is okay?
May I interrupt? It's 10:15. We have 3 speakers on the 6th and interrupt. Is Lays upon this here? Or anyone representing her group? No? Okay. So you can continue.
Okay.
Make sure that if you're in other sessions at 10:15, it's 10:15.
All right. Yeah, please let me know. If I can go fast or I can go slow. So whatever. Okay, thank you. So, and you can see the activity is really good stand after that. So that's Michael actually collecting a lot of data. But today, for this presentation, I'll be talking mainly the forest productivity, like hay production, then stem to leaf ratio, and then nutritive value and economics of this. And then these are the harvesting schedule. So in general, we harvested the plot established in 2019. Now we start harvesting 2020 and 2021. And every year we have 4 harvests. In Wyoming condition, we cannot go more than 4 harvests. If we have 3 harvests, we are really happy. But in general, we don't go more than 4 harvests. So you can see here is monthly harvest, June, July, August, and September. And this is early harvest, this is late harvest. So for example, 10th of June was first harvest, and harvest 1, and then late harvest was 7 days later of, so that's how every harvest happening in 2020 and 2021. So then, of course, data was analyzed with prog mix. So some results and discussion. So first, the soil. So if you look at this soil test results, the pH is 8.3. This is perfect for alfalfa growing. As I told, if you go below 6 or 6.5, then alfalfa is not a good crop to grow there. You have to increase the soil pH. Or if it is around 9, then it's not also good soil to grow alfalfa. So 8.3, neutral to around 8 is perfect condition for alfalfa growing. Organic matter always low in Wyoming condition and also in the West. It's less than 2%. Nitrogen was not bad. However, phosphorus was little low. Especially this one, potassium, as I told, we have a higher level of potassium as well. In general, in the West, it is recommended that if you have potassium 155 ppm or above, there is no need to add any potassium for alfalfa productivity. But this is a question now, 243 ppm. Is that worth applying potassium to the soil? That's the question, and we'll answer this question in a minute. And then we have also high calcium and magnesium as well. So now, the productivity first. So as we have several data, but I am presenting only summarized data here today. So this is phosphorus level, 0, 34, and 68, P2O5 per kilogram per hectare. So kilogram per hectare. So on the other hand, this is the productivity, and left-hand side, this is without any calcium, magnesium added. And here in the right-hand side, calcium and magnesium was added. And if you look at, and this is the blue bar, this is the late harvest, and the black dot is the early harvest. So as expected, you can see here, the late harvest always have higher productivity compared to early harvest. That is expected. However, if you look at this, this is early harvest, you can see as potassium level, phosphorus level increase, the productivity continuously increase. However, for late harvest, you can see after 34, there is no effect. It's actually started to decline. And that's true for also with calcium and magnesium addition to the soil. And then, when this is potassium, the same treatment like increasing level of potassium with calcium, magnesium, without calcium, magnesium, with calcium and magnesium. Very similar trend for without calcium and magnesium. But if you look at with calcium and magnesium, interestingly, there was no difference between early and late harvest. That means increasing level of potassium increase the productivity, no matter whether it is early or late harvest. Then what happens in combination of calcium and phosphorus and potassium in addition to calcium and magnesium without calcium and magnesium? Very interesting results. If you look at this here with calcium and magnesium, you can see both early and late harvest, combination of phosphorus and potassium, both continuously increasing the productivity. However, when we add calcium and magnesium, this is started to separating. That means calcium and magnesium influencing more uptake of potassium and phosphorus probably. As a result, the productivity started to increase. It's better. Thank you so much. So that's clear indication that combination of phosphorus and potassium in addition to calcium and magnesium is doing better job compared to only phosphorus or only potassium. Now, most important factor is how much productivity we get from each of the treatment. So this is the whole treatment. As I told, we have 18 treatment combination from control to the highest level of all the nutrient elements. And these are the total productivity. And now, what are the percentage of yield increase? If you look at this compared to control. So this is the highest increase came 41% from only combination of phosphorus and potassium, the highest rate. And then when we add even calcium and magnesium, it's only 33% increase. That means we don't need to add calcium and magnesium, but however, there should be sometimes some soil where we have more calcium and magnesium. In that situation, maybe we have to be careful, we might need to add more potassium and phosphorus in the soil to get the maximum benefit. How about late harvest? This was early harvest, and late harvest, very interesting, when the highest percentage of is more than 50% increase when you have all four combination of nutrients, clearly indicating that for late harvest, we need to add more potassium, phosphorus in addition to calcium and magnesium if we don't have calcium and magnesium in the soil. So also only phosphorus and potassium combination is only about 38% yield increase. Still, this is significant. So now how about nutritive value? In general, it is reported that calcium, magnesium, or addition of phosphorus and potassium has no effect of the quality of alfalfa. That's true. This is published data. Our results also suggest there was no effect. These are all the quality parameters. CP is crude protein, the neutral detergent fiber, ADFA acid detergent fiber, the total digestible nutrient, then also in vitro dry matter digestibility and relative feed value. These are all indices of forest quality. So you can see here there is no effect of 18 treatment combination of forest quality. This one sense is very good because there is no negative influence of any of the nutrient combination of the nutritive value of alfalfa. There was little effect of early versus late harvest only for neutral detergent fiber and also for relative feed value, but in general, there is no effect of nutrient of any of the treatment. How about stem to leaf ratio? Because this is where we can expect if we have more leaf to stem ratio, higher quality. However, we don't see any effect on those. That's the reason why we did not see any effect of any of the treatment combination. And that's really good thing that there is no influence on not only stem and also the quality of alfalfa. So now the most important component, that's what the producer will be interested to look at all those. So we did some economic analysis, including the planting time to all the products we use, including fertilizer, harvesting and all. And then we calculated how much, and also we keep the consideration of inflation as well. So in general, the production cost of both years over $350. And then we also include the cost of capital, 5%. And then the total production cost over about $370 each year. And then the hay price for both 2 years. This is the hay price we just used. And then expected revenue was around 585 first year, and second year was 554. And then the profit margin was that the production cost minus the revenue, then that will give you net profit. And that was first year was $200, and the second year was $182. That's really good from this. But how about if we look at each of the treatment? So when we consider each of the treatment as an independent premise, then what would be the production cost and net benefit of each of the treatment? So then you can see here, this is the total production cost, each of the treatment. The highest, of course, is more than $3,000. because we used all the highest rate of everything. So then, and only combination of P and K, we have about $2,800. So then the total revenue again, the coming, because of the higher productivity is about close to $5,000. That's really very high. And only if you use only P and K, still it's about 4,700. That's very high from this statement combination. So the profit margin would be the production cost minus the total earning. And you can see here, with this combination, this is the highest, about $2,000. And then the second, this is also when you have this combination with P and K and calcium magnesium, this is the second, almost $1,500. And what I am saying here that if you add only phosphorus and potassium combination, there is no difference actually, it's almost same. So even only if you use phosphorus and potassium, you can make a lot of money from there too as well. So in summary, so no doubt that alfalfa productivity and economic profitability can be increased through the balanced application of phosphorus and potassium. But you have to keep consideration in mind that harvest time play an important role. I showed that this, specifically in the early harvest, high rate of phosphorus and potassium are needed. On the other hand, if it is late harvest, moderate level of phosphorus and potassiums are needed as well. So also there is an interaction effect of P and K, and we have to make sure that we consider those effects as well. So also another factor we need to consider, I am not considering advising producer to go and apply calcium and magnesium, but this is an indication that if your soil has high level of calcium and magnesium, please keep in consideration that you might need to add more phosphorus specifically. So what would be the recommendation? It would be recommended that we should revisit and update our existing potassium guide that may be 100 years old or 50 years old, and to update that one, and along with the soil test results. So I'll stop it here, and I acknowledge all my team members. And I'll take, if you have also funding bodies, if you have any question, please feel free to ask. Thank you.
Is there one question that you might have?
Yes.
What kind of texture soil? Because we found that you've done similar things in alfalfa, and then we actually changed the critical level to over 200 instead of 150 because the smectite clays, they absorb potassium. So do you have that problem maybe too?
Yeah. So Marisol was asking about is there any problem with 155 versus 200 ppm of potassium level because of the soil structure and texture as well. Yeah, we have issue too. It's only one location. We have several locations. Even this study was conducted in 4 different states. And we have several issues, similar issue as well. That's correct. Any other questions?
Okay. Very good. Thank you, Anua.
Thank you.
All right, our next speaker will be Fernando Ortega Close from Chile. And the next speaker is also here, so you'll have 15 minutes.
Okay.
Please. And it was over here. Is correct?
Yes.
Okay.
Okay. Thank you very much, Alan. So this is the title. This research was conducted together with colleagues from the Universidad de la Frontera. I have been breeding red clover for the last 35 years, and we have made quite a big improvement in terms of persistency, survival of plants, and forage yield. So this is the first red clover variety of Chile, Quiniquelinia, and that was bred by my predecessor. Then we bred this variety, Red Quilinia, and later this Super Quilinia. So we have improved quite considerable the persistence of plants by using a practical approach, selecting in the field for in different environments for survival of plants and forage production. So in parallel to the applied breeding program, we have been doing some basic research in order to understand why some lines or varieties do have a better survival of plants. So this is the general pattern of the red clover growth in irrigated trials and dryland trials. This is with a spring sowing. So usually we have the highest forage yield in the second season, and then it declines. In dryland conditions with autumn sowing time, usually we have the highest forage yield in the establishment year, and then it declined. And why does it decline? Because we lose plant population. So in the red line, you have the plant population, the average plant population in the first year, second, third, and fourth. So with irrigation, by the end of the second or third year, we already have a considerable decline in plant population, and that is highly correlated with the reduction in forage yield. So yield and persistence is a quite complex trait to improve. It is affected by many factors, the genetic of the variety, and the interaction with pests, many pests and diseases, the competition of the associated species, management, and environmental conditions. Within the pests, the main one in Chile is the red clover borer, Ilestrinus obscurus. So we have been studying why some plants are more attractive to the red clover borer and why sometimes some plants are less attractive. So we have studied the volatiles because the insect flies and lay the eggs in the base of the plant. We have also studied fatty acids. With more intensity, we have been studying isoflavonoids, especially formaminonetin, and the relationship with the insect. So the object of this research is to study the relationship between the phosphorus available in the soil interacting with mycorrhiza over formaminonetin concentration of shoots and roots. So we ran one experiment at Carillanca Research Center. We established in a greenhouse, and then we moved the pots to a growth chamber with 24 and 18 centigrades day and night, 14 hours of light, 10 hours of dark. We used these pots, 6-liter pots with agricultural soil, 20 centimeters deep. So we established 16 plants per pot using a Super Quilinia, which is a diploid cultivar. So we established 3 levels of P, 10, 17, 24, and 2 levels of mycorrhiza with inoculation and without inoculation. We use a completely randomized design with factorial arrangement, and we established 2 complete and independent sets of pots in order to run the destructive sampling. We managed the soil water availability by weighting the pots. So a destructive sampling was performed twice. First, 21 days after moving the pots to the growth chamber, and the second one, 22 days after the first evaluations. So the plants were separated from the soil, washed, and after that, we cut the plant at the crown level. And we stabilized the samples by using liquid nitrogen, and later on, we did the lyophilization. We evaluated the colonization of the mycorrhiza. We also evaluated the chlorophyll content in the leaves several times, the plant height and root length, the yield both of the aerial and root section, and of course the formulating concentration in shoots and roots. This is a summary of the ANOVA of the first sampling date and of the second sampling date. So in the first sampling date, the main factor was the phosphorus level. It was quite significant, affecting the growth parameters and the formulating concentration. And the mycorrhiza affected the formulating concentration. In the second sampling date, again, the phosphorus was the main factor affecting growth and formulating concentration, and there was an interaction of the P and mycorrhiza for the root formulating content. So the chlorophyll content increased with the phosphorus levels, as it is shown here for the first sampling date and for the second sampling date. And in terms of biomass, we have here with the green color, the biomass of the shoots, and with the light brown color, the biomass of the roots for the first sampling date and for the second sampling date. So the phosphorus increased the both the shoot and root biomass production, both in the first sampling date and in the second sampling date. The formulating content decreased, the concentration decreased when we applied more phosphorus, both in shoots and roots. As expected, the formulating content in the shoots was higher compared to the roots because the formulating is synthesized in the shoots and then is translocated to the roots. So the inoculation with mycorrhiza increased the formulating concentration in the first sampling date compared to non-inoculated treatments, both in shoots and roots. And in the second sampling date, again, the phosphorus, when we increased the phosphorus, the formulating concentration in shoots decreased. And in terms of the interaction of mycorrhiza and phosphorus, something strange occurred. Perhaps this is because the roots already reached the bottom of the pot and the growth was already affected. So the main conclusions is that P and mycorrhiza did affect the formulating concentration and biomass production of red clover, especially the phosphorus. The higher concentration of formulating was obtained with reduced P and with mycorrhiza inoculation. By contrary, the biomass production increased with P and mycorrhiza inoculation. So in practical terms, and thinking about production and formulating concentration, the median level of P with mycorrhiza inoculation shows good compromise between biomass production and formulating concentration. And future research will consider the validation of the results in field trials and testing against the Elastinus obscurus, the red clover borer. Thank you very much.
Fernando, anyone have questions? Next question here.
Did you measure any other isoflavonoids besides hormone?
Not in this trial. We have done in, if we have measured other isoflavonoids, not in this trial. Yes, in other trials, yes, but not in this trial. But formaldehyde has usually been the most important in terms of concentration.
Other questions?
Yeah, when the plant's getting stressed, the secondary metabolism is high, so that's maybe because the shoot growth is decreasing and then secondary metabolism is increasing. Is it that the shoot growth increases directly
So you're explaining the yes, okay.
Measure it in under irrigation and non-irrigation
Yes.
condition, right? Is it possible that formula
So
increase the non-irrigated condition? For instance, water deficiency could be also increased.
we evaluated the irrigation. Yes, she's asking if when you stress the plant, usually formulating content increases. So she's asking about irrigation. Okay, we presented a paper in the last Congress regarding irrigation, and we didn't get that result. So in the other paper, in the other research, dryland conditions did not increase the formulating content in our trial.
Fernando, the injections, I would expect if you're increasing the phosphorus level, that the effect of the AMF, the mycorrhiza, will be less. You say your decolonization counts. Did you see any reduction on colonization of AMF at higher phosphorus levels?
No, we tested the colonization in both with mycorrhiza and without mycorrhiza. In both of them, we got colonization, similar colonization. Perhaps once were the native mycorrhiza, and the other one did mycorrhiza. Okay.
Very good. Any other final question? Very good. Thank you again for your presentation. Okay, Martin. I have to find your presentation here a bit. Martin Harmer. And it does work. You can use either one. Okay, very good. And there are plenty of seats. Okay, I saw some people. Well, what happened? Okay, we'll have to go here to. Good luck. Good luck. Here it is. Is it it? Is it it? No. Okay. Oops. Can we go back? Is it this beginning? One more. Yeah? Okay.
Yeah, good morning, folks. Thanks for your interest in my research. My name's Martin Harmer. I'm the Australian Research Manager of a company called DLF Seeds. And I'm going to be talking to you guys today about some research I did into improving the nitrogen use efficiency and uptake of perennial ryegrass using a epicloe fungal endophyte called AR37. Just an overview of what we're going to be talking about today. We'll cover the background briefly. So what's an endophyte and a primer on what's a marginal response. We'll talk about the methods, results in both in the yield response to nitrogen and the nitrogen percentage response that we observed. And then we'll finish up with what I think might be some of the economic and environmental implications of the findings. So just a primer for those who've forgotten since uni, for Economics 101 at uni. So marginal responses, what are they and why are they important? So a marginal response is the change in an output in response to a unit of input. So in this case, our unit is kilograms of dry matter per kilogram of nitrogen. For instance, you throw on a kilo of nitrogen and you get 12 kilos of dry matter off. Marginal responses in fertiliser are often characterised by diminishing marginal returns. So each subsequent unit applied is less effective than the unit prior. And to maximise profits, farmers should keep ramping up the application of fertiliser until the marginal response equals the marginal revenue. So here's just a hypothetical marginal response curve that I pulled from Dairy New Zealand's website, and you can see different seasons for perennial ryegrass. And one of them in winter, 25 kilos, you've hit a 7-to-1 response. We're still getting 12-to-1 in spring. So in these different seasons, you would rationally use a different amount of nitrogen. So what is an endophyte? Briefly, for those who are new to the topic, so it's a co-evolved symbiotic fungus that lives inside the plant. This fungus synthesizes a range of toxic alkaloids that are toxic to insects and animals, and recently patented novel endophytes that have been invented that don't produce the toxins, the animal toxins, but still produce toxins that are effective against insects. The adoption of these in Australia and New Zealand has been excellent. AR37 is virtually necessary to get to the top of our VCU and forage value index systems. Adoption in North American grazing systems has been so-so, and they remain illegal in Europe. So briefly, fungus inside a plant makes alkaloids. Alkaloids protect against insects and animals. So, not all endophytes are created equal. Don't have time to go through all of this, but different endophytes produce different metabolites or alkaloids. And the one I'm going to be talking about today is AR37. AR37 produces a novel group of compounds called epoxyxanthotrins, and importantly, it doesn't produce lolitrin B or ergovaline, which is why there's been such fantastic uptake by the New Zealand and Australian dairy industries. So I'm going to be comparing essentially the impact of these epoxyxanthotrins against a ryegrass plant that contains no endophytes, so no alkaloids. Methods: 3 replicates, nitrogen applied after every second harvest, nitrogen rates of 0, 20, 80 and 160 kilograms per hectare. We did tissue nitrogen on all plots at every cut with NIR. We did full plot harvest with subsampling for dry matter percentage. We irrigated over the summer to promote growth. We're a Mediterranean climate, it stops raining in summer. We collected data for 3 years. The perennial ryegrass cultivar we used was called Base. It's a perennial ryegrass cultivar, it's a tetraploid, and it's northwest Spanish genetic origin. So we get really good winter growth rates. And the treatments, I suppose, AR37 had 97% infection, and the nil treatment had 2% infection. So we did a good job of killing the endophyte out of the nil treatment. So we'll jump straight into the results. So endophyte did impact the nitrogen response function of the perennial ryegrass. The benefit of AR37 we found was consistently positive over time, and here I've shown a graph from 1st of December 2015. And in this example, you can see the open circles and the dashed line. That's the response of the nil endophyte cultivar to nitrogen, and it has a marginal response of 10.4 to 1. AR37, inside the same variety, it's doing 16.9 to 1 marginal response. So the AR37's benefit on this occasion was an additional 6.5 kilograms of dry matter per kilogram of nitrogen in marginal response. So I'm briefly going to touch on why have I fitted linear equations, because anyone in the audience who's got any clue about fertiliser response functions knows that that's not how the world works. And you'll rightly pull me up on it, and I agree with you. So I believe that due to the nitrogen drawdown that we had, we're running a cut and carry system. We're actually observing a very, very early stage of the nitrogen response function, and that we weren't observing the part where you get your asymptote. So just to briefly explain that, this is your marginal response function. I think because we had so much nitrogen drawdown running a cut and carry system, I think we're observing the part in the green circle. Occasionally you might see a bit of an asymptote, but we're observing the early bit. So sadly, 3 years of research, we didn't get to the bit where it asymptoted. So I have no idea what it does up there. I have some theories, but yeah. So I agree with you. Linear regressions are wrong, but if you investigate very early part of the curve, you get a linear regression. So how did these positive impacts of AR37 vary over time? So here I've graphed the percentage difference in the solid black line and solid circles over time, and the absolute difference in kilograms of dry matter per kilogram of nitrogen over time for the 3 years of data. And the benefit varied, so it went from 0.2 to 6.5 kilograms of dry matter per kilogram of nitrogen, or it ranged from a 4% to a 62% improvement in the marginal response. We found that the benefit increased every summer and autumn. So those spikes you can see in the benefit that we observe were recurring every summer. And sadly, our irrigator broke down in the summer of 16-17, so I don't have data, but I'm pretty sure we would have got a spike there. So we see the benefit coming in each summer and autumn and it waning each winter through early spring. So I felt the logical thing to do then was to cluster the data by seasons and analyse the benefit seasonally. So that's what I'm going to talk about next. So here's your seasonal response functions: summer, autumn, winter and spring. And in the table we've got the differences between the response functions. So you can see that the magnitude of the differences between seasons is actually not that great. So the worst benefit we got was an additional kilo of response in spring, through to an additional 2.3 kilos in autumn. Again, you can see the benefits more in summer and autumn than winter and spring. And you can see that the percentage increase in the response of the pasture to nitrogen is quite significantly higher in summer, so a 92% better response to the applied nitrogen, 36% better response in autumn, and in winter we have a 10 and 17% improvement. Winter and spring we have 10 and 17% improvement in the pasture's performance. So averaged over all of the harvests, all the 3 years worth of data, we had an additional 2.1 kilograms per marginal response, or a 30% improvement in the efficiency with which the nitrogen was used. So why do we think that these responses might be changing seasonally? Well, we know in a lot of high rainfall pasture zones in Australia where perennial ryegrass or continental tall fescue is used, we have a heap of this root-feeding insect called root aphid, and there's research that demonstrates that the populations of these root aphids vary seasonally. So I think what's happening is that in summer and autumn, the root aphid is going to town on that plant. It is grazing the root system, and thus AR37's ability to keep that root aphid at bay is causing quite the grass to be healthier and able to better respond to the nitrogen. So this is that one little green box there is all I'm going to say about the nitrogen percentage and the environmental benefits. So we found that AR37 didn't affect the nitrogen percentage of the foliage. So at 80 kilos or 160 kilos, the nil line and the AR37 line almost invariably had the same nitrogen percentage as each other. So we can conclude from that AR37 did cause an improvement in the uptake of applied nitrogen, but the mechanism wasn't the plant having higher nitrogen percentage. It was simply driven by the improved yield at any given nitrogen input level. So by inference, the same improvement will be observed in nitrogen uptake, in that 30% more of the applied nitrogen on an annual basis ends up in the plant. So my final slide, coming in at the 10-minute mark, which is good, are the implications. So economic implications. So AR37 consistently increased the ryegrass's marginal response to nitrogen. The biggest benefits that we observed occurred in summer and autumn, consistently in summer and autumn, but they weren't inconsequential in winter and spring. So AR37 reduces farmers, in our environment, AR37 reduces farmers' marginal cost of feed by 30% in the range of nitrogen application rates that we investigated. So what I find interesting, and I'm disappointed that I wasn't able to capture data on, is did AR37 cause the marginal response to diminish at higher N input levels? And that would be really interesting to know. I suspect it does, but I can't prove that with the data I've got, because if it did, it would increase the amount of nitrogen that farmers were able to profitably utilise on their pastures. So they'd be able to, the nitrogen lever would be an even bigger lever for them. They could apply higher rates and get even more grass out of it. So the environmental implications, so I suppose AR37 increased the amount of applied nitrogen that was utilised by the ryegrass, did so by 30% on average, and increased N uptake in autumn and winter, I believe, would likely reduce leaching. There's a fair bit of research out there that shows if you've got a plant mopping up that nitrogen in autumn and winter, that mineralised nitrogen from autumn, it doesn't escape from the root zone when you get leaching. So I think that there could be some environmental implications there. And by driving greater N uptake AR37 might have implication for denitrification. I mean, if it's in the plant, it can't denitrify. So, and my final point for any European regulators who are in the audience is that, you know, given the demonstrated environmental and productivity benefits of AR37, the sort of Europe's legislative opposition to endophytes, given you're really concerned about nitrogen and the environment, doesn't seem particularly tenable. So, yeah, thanks for listening.
Some questions?
I'm from the United Kingdom, which is no longer part of it. But I also was involved at the time of Yaxin 2, which I think was a New Zealand variety with endophyte. Seed crops were killing horses because the hay was being baled and fed to horses. So I guess that's where Europe's dislike of endophytes came from. We are seeing bacteria endophytes coming in now. So we can cut to the chase. What other pests do you think AR37 would help?
Oh, I hope.
Would you mind summarising a little bit?
Okay, so the question was, what other pests can AR37 keep at bay? All right, if there's any endophyte experts in the audience, chip in. I think it does a great job against African black beetle, Argentinian stem weevil. What else have we got? In New Zealand, piranha, and maybe, have I missed anything, endophyte experts? Yeah, so there's a...
I think the messages that in Europe there appeals to messages.
Yeah, 100%. I wouldn't suggest you're going to get the same result. In some other countries in different agroclimatic zones, we don't see the same benefit. In some agroclimatic zones, like northern New South Wales, there's more benefit. So yeah, I'm not suggesting the same result will occur everywhere.
Most inversions have a list of insects and they protect you, so
Yep.
go online and look up the sync count.
Yep.
Trouble is we don't have one
Yep.
in the UK.
If I recall correctly, endophytes are also associated with increased water use efficiency. So could that not also explain why you're seeing greater production but no greater nitrogen uptake? And also when you're seeing that impact was seen to be much greater in summer and autumn, which would tie in with, better water use efficiency in the middle of an Australian summer.
Yeah, well, I suppose if you lay water application over this instead of nitrogen application, you divide the water application by the yield, you get better water use efficiency. So, and I think the same argument could be applied to phosphorus or anything else you apply. I think all your inputs are better utilised. So the mechanism, not sure. Yeah.
There was a question here. We have, this will have to be the final.
Yep.
Did you compare with other endophytes as well, or just AR37 and no?
We also have a variety with AR1. It's a different cultivar, but it's AR1 endophyte, and that was not particularly effective, and we know that based on a history of that endophyte at the site. And yeah, that was the only other endophyte that we tested at that site. So we do have data on other endophytes, but they're confounded by cultivar.
Okay, one other remark. I'm not from England, but from Europe. There's no regulations in Europe.
Okay, well, it's just, yeah.
Okay.
Thanks for your time.
We'll have to move, but if you can make your question short.
Does he access any below ground responses? Any below ground responses? Did you access any below ground responses?
We assessed. We have a data set on the. We have a data set on the nitrogen that's in the soil. We didn't assess the root systems, but we have data on the nitrogen that was within the soil. So we will get around to publishing to show that there's less nitrogen in the soil. So, yeah.
Very good. Thank you, Martin. Okay. Thanks so much. We have one final presentation. Our final speaker is not here, but Lachlan Ingram from Australia will give our final presentation. Would you like to use the podium? Yes?
Yep. So thank you. So thank you very much for turning up this morning. So my name is Lachlan Ingram. Unfortunately, Matt Newell couldn't make the conference due to bureaucratic nightmares of Australia. So he's asked me to do his presentation. So I'm going to be talking about the effects of nitrogen rate and plant density on grain components of intermediate wheatgrass and mountain rye. So I guess we could really sort of sum up, the reality is that if we generally observe, most ecosystems, including, surprise, surprise, grasslands, tend to be composed predominantly of perennial species, and they're generally, relatively speaking, pretty diverse. And as a result of that, they tend to be highly stable. They don't tend to change much. You can see that periodically, but under most set of circumstances, they're relatively stable. And so a grazing system, grasslands are obviously a graze system also, so that sort of then feeds into our interactions. So I guess we're thinking about most of our cropping agriculture. Generally speaking, it is relatively, while our cropping has been incredibly phenomenally successful at feeding the population's broad rule, it has been generally doing it as an annual crop and grown in a monoculture. And also we seem to have pretty much concentrated our crops around three major crops, which, as you can see from this map from FAO, is simply it's pretty much provided by maize or corn, wheat and rice. So we essentially have a very, very relatively simple system that is highly dominated by three major species. So while that system has worked very well, it does have some issues. It's been obviously very successful, but it's come at a cost that we now have gone from a relatively diverse system that is relatively resilient to a large degree of changes that it will deal with on a day-to-day basis, but also we're increasingly reliant to maintain those annual crops on a range of external energy sources and large amounts of obvious inputs, fertiliser, etc. So we also then have the issue is that, in a more traditional native system, that we have a relatively stable system that has a range of succession. Most ecosystems will go through that successional process. However, in a cropping system, we are essentially stuck in a successional annual loop, basically. We keep every year, we are basically changing it back into a primary cropping system, essentially, using a range of annual species. So we keep just repeating that process because we're generally using a range of fallow methods, either mechanical or chemical, to maintain in that system. So as a result, we have that issue where because of those two, we're getting a high level of disturbance. And so particularly, I doubt Australia is any great different from many other areas of agriculture in the world. We have had massive issues in terms of decreases in soil quality, large amounts of soil erosion. We've also, obviously we're impacting on the soil health because of this repeated tilling and fallowing process. We've impacted on, we've lost large amounts of soil carbon, etc. as a result of that. And then also, we've also then impacted greatly on our hydrology because particularly in Australia, we have removed a lot of trees out of the system. So we've very much upset our water flows, essentially. So one way we might be able to deal with some of these issues is trying to incorporate a range of perennial forage crops or crops into our system. So we might perhaps, we might be able to get back and improve to a more perennial and diverse system without hopefully losing too much of our production around a cropping system. So one way we can do this is we can domesticate some of these perennial grasses as grain crops. So I'm going to be talking today about intermediate wheatgrass and mountain rye, again both perennial species. So these have essentially been originally just a perennial forage grass, and then over several cycles, standard breeding, they have been selected for grain size and grain yield to varying degrees. So for intermediate wheatgrass, this has been, I think it's in Kansas, the Institute of Land Systems, I think it's called. They've been doing some work in this, so it's, they've come out with a breed called Kernza. And so Kernza has been used under a variety of products available, right, including cereal, bread, crackers, pasta, essentially, beer and whiskey. Of course, there's going to be alcohol involved somewhere. So it's been reasonably successful, as I understand it, and has had some commercial uptake in the US. Also with mountain rye, a little bit more simple, mainly in terms of flour. There has been some production on it, beer, of course, and a range of other foodstuffs. So while they have been occurred in the US, neither of those species have really been used or trialled in Australia to any great degree. So this was work undertaken by Matt with New South Wales Department of Primary Industries, and so just to try and get some understanding of how they might do in an Australian system and how we might need to optimise these under the Australian context. So this was some work that was done, was originally planted. The first trial was done in April 2020, was planted, and then was harvested in February 2021. This was undertaken in Orange, so sort of central New South Wales, so a rainfall of around about 850 millimetres. So the two species, and then Matt was looking at three different densities, so 50 plants per metre squared, 100 plants per metre squared, and 200 plants per metre squared. And then three nitrogen rates, 0, 100 and 200 kilograms of nitrogen per hectare. And then the analysis was looking at tillering, grain yield, floret fertility and seed size, and plant height and lodging. So generally speaking, there was no interaction between the various crop types, so the intermediate wheatgrass and the mountain rye plant population or nitrogen, so as I'm just going to be talking about the main effects essentially. There were, however, significant main effects in regards to crop type, in regards to the mature tiller number. There was about a 70% increase in the mountain rye. There was also much greater seed weight, somewhat greater seed weight with the mountain rye. And as a result of that, there was a much greater grain yield from the mountain rye. For those who are not perhaps up to speed with general cropping in Australia, we would probably average broadly across Australia probably around about 1.5 tonnes of wheat per hectare. So in the general ballpark, mountain rye was getting something in that general order basically. And also remembering the fact that we have been doing wheat breeding in Australia for 100 years, whereas we've done pretty much nothing with mountain rye. So as a first shot, it's getting fairly close to what you would find in a standard cropping system in Australia. So plant height was generally higher with the intermediate wheatgrass and the mountain rye. One of the big differences is that with the lodging score, the intermediate wheatgrass was generally quite upright. So for the lodging score, a value of 0 basically meant that all the plants were standing. A value of 10 meant that all the plants had basically lodged and were lying on the ground. So clearly, intermediate wheatgrass generally stood up the whole time, whereas the mountain rye had relatively high levels of lodging, so sort of in the order of about 45% of the plants had actually lodged. So the floret fertility, again, mountain rye was much higher than the intermediate wheatgrass. However, there was a much smaller number of seeds per spikelet. So, with regards to the nitrogen response, generally speaking, there was no real changes from 0 to 100. We did see an increase in 200. One of the reasons we may not have been seeing a big impact on the tillers is that this was a relatively high nitrogen site, so we may have basically crossed that threshold that basically these plants weren't being held back by nitrogen per se, but were being held back in Australia more likely by phosphorus or possibly sulphur. So again, the nitrogen response may not be what you would see in other locations. However, in spite of that, we generally saw a decrease in yield as nitrogen increased, which perhaps again is not expected, certainly in an Australian context. But again, going back to what I mentioned previously, nitrogen was quite high at this site, and there has been observations that if you increase nitrogen, broadly speaking, that you might actually see a decrease over time at very high levels of nitrogen. So this may just be a specific site response rather than a general response to nitrogen. So in conclusion, the main effects were largely driven by crop type initially. There was very little effect of the plant population or nitrogen. In fact, in some cases, we're actually seeing a decrease in nitrogen in response to high levels of nitrogen. And we just need to, essentially at this stage, because this was the first year of this trial, we probably do need to monitor it, because again, being early as a first year of a perennial grass system, it's not unreasonable to expect we might see some changes as the plants get older. And at this stage, mountain rye has had no selection, certainly in Australia, for any of these grain yield characteristics. So, it's reasonable to expect that with a little bit of breeding and ongoing work in this area, that we could potentially increase some of these factors. And again, generally speaking, because of the much higher grain weight that we found with mountain rye, it is reasonable to expect that with a bit of breeding work and increasing domestication of mountain rye, that we could easily sort of ramp up the grain yield, and it would more probably closely match we'd find wheat. So it has some real promise, particularly going back from an annual system into a perennial system, and it would tie in very well with what we call our mixed cropping systems in Australia, which are a combination. Typically, we'll put a system into pasture for a period, into crop for a period of years, and then we'll turn that into a pasture system. So again, this is a quite common system. So again, if we can get some more perenniality into our annual cropping system, it's one way we can start trying to improve some of the soil and water issues that we are seeing in Australia. So I'd just like to acknowledge New South Wales Department of Primary Industry, and this research was funded by Meat and Livestock Australia. Thank you very much, and any questions? Yes.
Maybe I missed this. Thanks. Hi, maybe I missed this. Did you mention if you used a specific population breeding cycle or variety of intermediate wheatgrass?
No, so these varieties are from the US, but I believe they are not the latest varieties that are currently available. So that was being brought to you a few years ago. And as I said, there's been no breeding being sort of done in Australia. There's obviously been breeding work done in the US.
Yeah, thank you.
Yeah, question. Is the intent? Have you thought about like winter grazing on these? Like, what's the strategy and the utilization of I guess the straw or the forage after grain harvest?
Mm-hmm. So at the moment, this is just sort of a first cut just to get some idea. But yes, using something like a dual-purpose system is a potential, because those dual-purpose systems are used a lot in Australia. We have a whole range, and they're very commonly used. So again, it provides another tool to farmers in that, if you have a relatively good year, you might be able to graze them and then crop them. If it's a really bad year, like a drought, perhaps you just end up grazing them. Or if you may just want to just have them there, sitting there, then to crop them on an annual basis. So it gives the farmers sort of more options as to, depending on the climate and their particular system, as to how they can be used. And as I said, in regards to breeding, at this stage there's no work done on it all in Australia.
Any other questions? Well, Lachlan, thank you so much. I have one short question about
Yes.
Any effects on weed control. I mean, these are varieties that you brought in,
Yep.
or a common variety. Was any herbicide being able to be applied?
I couldn't tell you, I'm afraid, Alan.
Okay, all right, very good. And thank you to Kendall for helping me out in the session, and thank you all for attending and having some good questions, and the presenters as well. Thank you so much.